I want you to do something different. I want you to find the most comfortable position you can. Maybe you are lying in bed right now. Maybe you are on your couch. Maybe you are sitting in a chair with your headphones on and the lights turned low. Wherever you are, I want you to take a deep breath. Breathe in slowly through your nose, hold it for just a moment, and then let it out gently through your mouth. Do that one more time. Breathe in, hold, and release. Good, because tonight we are going to go on a journey together. It is not a journey to a distant country or a journey through some action-packed adventure. No, tonight, we are going to travel through one of the most fascinating landscapes that humanity has ever created. We are going to explore the world of machine learning. And we are going to do it slowly, calmly, like a quiet conversation between two friends sitting under a sky full of stars, talking about how the universe works. There is no rush. There is no exam at the end. You do not need to memorize anything. If you fall asleep somewhere in the middle, that is perfectly fine. In fact, that might be exactly what you need. But here's what I promise you. If you stay awake, even for just parts of this journey, you will understand machine learning better than the vast majority of people on this planet. You will understand how your phone seems to read your mind. You will understand why Netflix somehow knows exactly what you want to watch after a long day. You will understand how doctors are beginning to use invisible algorithms to catch diseases earlier than ever before. You will understand how scientists are using these same ideas to search for new planets in distant galaxies. And you will understand all of this not through complicated jargon or confusing equations, but through stories, through curiosity, through the simple wonder of asking how things work. Let me begin by asking you some questions. You do not need to answer them out loud. Just let them float through your mind. Have you ever picked up your phone, opened a search engine, and started typing something? And before you could finish your sentence, the phone already knew what you were going to say? How did it do that? Have you ever scrolled through a social media feed and noticed that the app seems to know your mood? That after a sad day, it shows you comforting content, and after an exciting day, it shows you energetic content? How does it know? Have you ever wondered how your email service somehow catches almost every spam email and puts it in a separate folder, even though spammers are constantly changing their tactics? Or, here is one that might really make you think. Have you ever wondered how a self-driving car can navigate through a busy city street, avoiding pedestrians, reading traffic signs, making split-second decisions, all without a human touching the steering wheel? The answer to every single one of these questions is machine learning. And the most remarkable thing about machine learning, the thing that makes it truly extraordinary, is that it was inspired by something you already carry with you everywhere you go. It was inspired by your brain, the very organ that is processing these words right now. The organ that is deciding whether to keep listening or to drift off to sleep. That organ is the original blueprint for everything we are about to discuss tonight. So tonight, we are going to cover a vast territory. We will start with the simplest question imaginable. What does it even mean to learn? And from there, we will travel through the history of how humans tried to teach machines to learn. We will explore the fundamental types of machine learning. We will dive into how machines actually process information, how they see images, how they understand language, how they make decisions. We will explore how machine learning is transforming healthcare in ways that will directly affect your life and the lives of the people you love. We will journey into space and see how these algorithms are helping us discover new worlds. We will wrestle with the deep ethical questions that machine learning raises about privacy, about fairness, about the future of work, and we will look at the cutting edge of this technology, at where it is heading, at the future that is being built right now, in labs and universities and companies around the world. All of it explained slowly. All of it explained calmly. All of it designed to either teach you something wonderful or gently guide you into a peaceful sleep. Either way, you win. Before we dive in, I want to ask you for something small. If you find this kind of content valuable, if you think that learning about the world in a calm, unhurried way is something worth supporting, then I would really appreciate it if you took a moment to hit the like button. It takes less than a second, but it makes a real difference. And if you are new here, consider subscribing. We explore fascinating topics like this regularly, always with depth, always with curiosity, always with the goal of making complex things feel simple and accessible. And one more thing, as you listen tonight, if any particular part of this journey sparks your curiosity, if something surprises you or makes you think, leave a comment about it. Tell me which part you found most interesting. Or if you fall asleep, tell me the last thing you remember hearing. I would love to know. All right, let us begin for real now. Let us start at the very beginning. Before we can understand how machines learn, we need to understand what learning itself actually is. And to understand learning, we need to understand the most complex object in the known universe. It is not a star. It is not a black hole. It is not a galaxy spanning 100,000 light years across. The most complex object in the known universe is sitting right inside your skull. It is your brain. Your brain contains approximately 86 billion neurons. That number is almost impossible to truly comprehend. So let me try to put it in perspective. If you counted 1 neuron per second, it would take you over 2,700 years to count them all. That is longer than the time from the founding of ancient Rome to today. And these neurons are not just sitting there doing nothing. Each one of them can connect to thousands, sometimes tens of thousands of other neurons. The total number of connections in your brain is estimated to be somewhere around 100 trillion. 100 trillion connections, each one capable of strengthening or weakening. Each one carrying tiny electrical and chemical signals that somehow, when put together, create your thoughts, your memories, your emotions, your entire experience of being alive. Now here is what is truly remarkable. When you were born, your brain did not come preloaded with knowledge about the world. You did not know what a face was. You did not know what gravity was. You did not know that fire was hot or that ice was cold. You learned all of these things, and the way you learned them is fascinating. Think about how a baby learns to recognize its mother's face. Nobody sits down with the baby and gives it a textbook on facial recognition. Nobody explains the mathematical proportions of a human face or the way light reflects off skin at different angles. Instead, what happens is much simpler and much more elegant. The baby sees its mother's face over and over and over again, in different lighting, from different angles, with different expressions. And slowly, gradually, the baby's brain starts to notice patterns. The shape of the eyes, the curve of the smile, the particular way this face looks compared to all other faces. Neurons fire together, and when they fire together, the connections between them get stronger. This is a principle in neuroscience often summarized as neurons that fire together, wire together. The more the baby sees its mother's face, the stronger those neural connections become, until eventually, the baby can recognize its mother instantly, even in a crowded room, even from across a long distance, even if she has changed her hairstyle or is wearing sunglasses. That is learning. At its most fundamental level, learning is the process of finding patterns in the world and strengthening the mental connections that encode those patterns. And this kind of learning is not just something that happens in early childhood. It happens throughout your entire life, every single day. When you learn to ride a bicycle, your brain is finding patterns in balance, in muscle movement, in the relationship between how you lean and how the bicycle responds. When you learn a new language, your brain is finding patterns in sounds, in grammar, in the way certain words tend to appear together. When you learn to cook a new recipe, your brain is encoding patterns about timing, about temperature, about the way ingredients interact. Everything you have ever learned, from the most basic skill to the most complex idea, has been your brain finding patterns in data and storing those patterns as neural connections. Remember this, because this is the core insight that made machine learning possible. The scientists who created machine learning did not start by trying to build something completely new. They started by asking a simple question. If the human brain learns by finding patterns in data and adjusting the strength of neural connections, can we build an artificial system that does the same thing? Let me take you a little deeper into how your brain works, because it will make everything about machine learning much clearer. Let us zoom in on a single neuron. A neuron is a specialized cell. It has three main parts that we care about for our purposes. First, there are the dendrites. These are like tiny branches that extend outward from the neuron, and they receive signals from other neurons. Think of them as the input channels. Second, there is the cell body. This is where the neuron processes the signals it has received, adding them up, weighing them against each other. Third, there is the axon. This is a long, thin extension that carries the neuron's output signal to other neurons. Think of it as the output channel. Now here is how it works. A neuron receives signals from many other neurons through its dendrites. Some of these signals are excitatory, meaning they encourage the neuron to fire. Others are inhibitory, meaning they discourage it from firing. The neuron adds up all of these signals, and if the total exceeds a certain threshold, the neuron fires. It sends its own signal down its axon, which then connects to the dendrites of other neurons, and the process continues. The crucial detail is this: not all connections are equal. Some connections are strong, meaning the signal they carry has a lot of influence. Others are weak, meaning their signal has little influence. And these connection strengths change over time. When you learn something, certain connections get stronger and others get weaker. This is the physical basis of memory and learning in your brain. It is elegant, it is powerful, and it is exactly this mechanism that inspired the creation of artificial neural networks, which are at the heart of modern machine learning. There is another thing your brain does that is absolutely critical to understanding machine learning, and that is pattern recognition. Your brain is astonishingly good at recognizing patterns, so good that you usually do not even notice it happening. Right now, as you hear these words, your brain is performing an incredibly complex pattern recognition task. It is taking raw sound waves, breaking them down into components, matching those components against stored patterns for language, extracting meaning, and constructing an understanding of what is being said. And it does all of this in real time, effortlessly, without you having to think about it consciously. Your brain recognizes faces in a fraction of a second. It recognizes objects, sounds, textures, tastes, and smells with remarkable speed and accuracy. It can spot a friend in a crowd of thousands, detect that something smells slightly off about food before you eat it, or sense that something about a situation feels wrong even before you can articulate why. This ability to find patterns in complex data is your brain's superpower, and it is precisely this superpower that we have been trying to give to machines. Here is a wonderful example of how powerful your brain's pattern recognition is. Have you ever looked up at the clouds and seen shapes? A face, an animal, a castle? That is your brain's pattern recognition system working overtime. Finding patterns even where none exist. Or consider optical illusions. An optical illusion works because it exploits the shortcuts your brain uses for pattern recognition. Your brain is so eager to find patterns that it can be tricked into seeing things that are not there, or into misinterpreting what is actually there. These quirks and imperfections in your brain's pattern recognition system are actually deeply informative for machine learning researchers, because artificial systems have their own quirks and failure modes that are sometimes remarkably similar to human ones. Let me connect this to something that might seem far away, but is actually deeply relevant. In the vastness of space, astronomers face a problem that is very similar to what machine learning engineers face. They have enormous amounts of data, images of millions of stars and galaxies, and they need to find patterns in that data. They need to identify which stars have planets orbiting them, which galaxies are colliding, which signals indicate something new and interesting versus something already known. For decades, astronomers did this by eye, poring over images and data, using their own brain's pattern recognition abilities. But the amount of data grew too vast for human eyes alone. And so astronomers turned to the same solution that so many other fields have turned to. They turned to machine learning. They built systems inspired by the human brain's pattern recognition, and they used those systems to sift through the cosmic haystack, looking for needles of discovery. And they found them. Machine learning has helped discover exoplanets, classify galaxies, detect gravitational waves, and identify phenomena that human astronomers had overlooked. The same fundamental ability that helps a baby recognize its mother's face is now helping us explore the universe. Now, the question that started this entire field, the question that has driven decades of research and billions of dollars of investment, is beautifully simple. Can we build a machine that learns the way we do? Can we create an artificial system that takes in data, finds patterns, adjusts its internal connections, and gradually gets better at a task over time? This question was first asked seriously in the 1940s and 1950s, and the journey from that initial question to where we are today is one of the most fascinating stories in the history of science and technology. So let us travel back in time. The year is 1943. The world is in the grip of the Second World War. In the midst of this global conflict, two men from very different backgrounds came together and created something that would eventually change the world. Warren McCulloch was a neuroscientist. He spent his career studying the brain, trying to understand how neurons worked and how they gave rise to thought. Walter Pitts was a mathematician, a largely self-taught genius who had been solving complex mathematical problems since he was a teenager. McCulloch and Pitts asked a deceptively simple question. Could the behavior of a single neuron be described mathematically? They proposed a model. Their artificial neuron took in one or more binary inputs, each with a weight representing its importance. The neuron summed up these weighted inputs, and if the sum exceeded a threshold, the neuron output a 1. If it did not, the neuron output a 0. This was incredibly simple compared to a real biological neuron. A real neuron has thousands of connections, operates with continuous rather than binary signals, and has complex chemical dynamics that we still do not fully understand. But McCulloch and Pitts were not trying to perfectly replicate biology. They were trying to capture the essence of what a neuron does, the fundamental computation, in mathematical form. And in doing so, they planted the first seed of what would grow into the vast field of machine learning. It is worth pausing here for a moment to appreciate the profound simplicity of what McCulloch and Pitts did. They looked at something unbelievably complex, the human neuron, and they asked what is the simplest mathematical model that captures its essential behavior. This act of simplification, of finding the core principle beneath layers of complexity, is one of the most powerful tools in all of science, and it is something that machine learning does extraordinarily well, finding simple patterns beneath complex data. In a way, McCulloch and Pitts were doing with their minds what machine learning does with algorithms. They were finding a pattern. Let us move forward a few years. The year is 1950. The war is over, and the world is beginning to dream of the future. In England, a man named Alan Turing, one of the greatest minds of the 20th century, publishes a paper that will become one of the most famous and most debated in the history of computer science. The paper is called Computing Machinery and Intelligence, and in it, Turing tackles a question that seems simple, but is actually profound. Can machines think? Turing was uniquely qualified to ask this question. During the war, he had been instrumental in breaking the Enigma code used by the Nazi military, a feat that is estimated to have shortened the war by at least 2 years and saved millions of lives. He had also laid the theoretical foundations for the modern computer. But Turing was not content with machines that merely followed instructions. He wanted to know whether a machine could truly be said to think. Turing recognized that the question "can machines think" is problematic, because we do not even have a clear definition of thinking. So he proposed an elegant workaround, a test that has come to be known as the Turing test. The idea is simple. A human judge has a text conversation with two entities hidden behind a screen. One entity is a human, and the other is a machine. If the judge cannot reliably tell which is which, then the machine is said to have passed the test. It is said to exhibit intelligent behavior indistinguishable from that of a human. Turing made some remarkable predictions in this paper. He predicted that, by the year 2000, machines would be able to fool a human judge about 30% of the time in a 5-minute conversation. He was somewhat optimistic in his timeline, but the spirit of his prediction has come remarkably close to reality. Modern language models can engage in conversations that are often indistinguishable from those of a human, at least in short exchanges. Turing also raised and considered several objections to machine intelligence, from theological arguments to mathematical ones, and his responses to these objections are still relevant and thought-provoking today. But perhaps the most important thing Turing did was to shift the conversation from the philosophical and abstract to the practical and testable. He gave the world a framework for thinking about machine intelligence that was grounded in observable behavior rather than metaphysical speculation. I want you to imagine for a moment the audacity of Turing's question. In 1950, computers were room-sized machines that could barely do basic arithmetic. The idea that such machines could one day think, or at least behave as though they were thinking, must have seemed like pure science fiction to most people. And yet Turing saw something that others did not. He saw the potential. He understood that the limitations of the computers of his day were limitations of technology, not limitations of principle. And he was right. The principles he articulated in 1950 are the same principles that underlie ChatGPT, Claude, and every other language model in use today, more than 70 years later. Now let us travel to the summer of 1956. The setting is Dartmouth College in Hanover, New Hampshire, in the United States. A young mathematics professor named John McCarthy has organized a summer workshop. He has invited some of the brightest minds in mathematics, computer science, and cognitive science to spend the summer working on a wildly ambitious project. McCarthy wanted to explore the conjecture that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. In the proposal for this workshop, McCarthy coined a new term for this endeavor. He called it artificial intelligence. The Dartmouth Summer Research Project on Artificial Intelligence, as it was formerly known, is often regarded as the birthplace of AI as a field of study. Among the attendees were Marvin Minsky, who would become one of the most influential figures in AI, Claude Shannon, who had founded the field of information theory, and Nathaniel Rochester, who had designed EM's first commercial computer. The participants were extraordinarily optimistic. They genuinely believed that significant progress toward human-level machine intelligence could be made in a single summer. They were, it turned out, spectacularly wrong about the timeline. But their ambition, their willingness to take on an impossibly large problem with confidence and enthusiasm, set the direction for the next 7 decades of research. It is important to understand where machine learning fits within this broader picture. Artificial intelligence is the big umbrella, the grand vision of creating machines that can think, reason, learn, and solve problems the way humans do. Machine learning is a subset of that vision. It is a specific approach to achieving artificial intelligence, one based on the idea that instead of explicitly programming a machine with rules for how to be intelligent, you feed it data and let it learn the rules for itself. As it turned out, this approach, the machine learning approach, would prove to be by far the most successful path toward artificial intelligence. Almost all of the AI breakthroughs you hear about today, from language models to image recognition to game-playing systems, are powered by machine learning. 1 year after the Dartmouth workshop, in 1957, something truly exciting happened. A psychologist at Cornell University named Frank Rosenblatt built a machine called the perceptron. The perceptron was, in a sense, a physical realization of the mathematical neuron that McCulloch and Pitts had described 14 years earlier. But it was more than that. The perceptron could learn. Rosenblatt had designed it with an algorithm that allowed it to adjust its weights based on the errors it made. You would show the perceptron an image. It would make a prediction. You would tell it whether it was right or wrong, and it would adjust its internal weights slightly to do better next time. After many repetitions of this process, the perceptron could learn to classify simple patterns. It could, for example, learn to distinguish between simple shapes, or between images on the left side versus the right side of its visual field. This was revolutionary. For the first time, a machine had been built that could genuinely learn from experience. The New York Times covered the story with a headline about an electronic brain that the Navy expected would be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. The hype was enormous, and the expectations were wildly unrealistic. But the core achievement was real and important. The perceptron demonstrated that the fundamental idea, building a machine that learns by adjusting internal weights based on errors, actually worked. The excitement around the perceptron lasted about a decade. Then, in 1969, something happened that sent the field into a long, cold winter. 2 very prominent AI researchers, Marvin Minsky and Seymour Papert, published a book called Perceptrons. In this book, they mathematically proved that a single-layer perceptron had fundamental limitations. Specifically, it could not solve certain kinds of problems, including a deceptively simple one, called the Zohr problem. Let me explain what the Zohr problem is, in a way that I hope is intuitive. Imagine you have two switches, each of which can be either on or off. The Zohr function says that the output should be on when exactly one of the switches is on, but off when both switches are in the same position, either both on or both off. This might seem like a trivially simple task, but a single perceptron, because it can only draw a single straight line to separate two categories, cannot solve it. If you try to plot the Zohr function on a graph, you will find that no single straight line can separate the on cases from the off cases. You need something more complex. This might seem like a minor technical limitation, but Minsky and Papert argued that it pointed to deep and fundamental constraints on what perceptrons could do. The impact of this book was devastating for the field. Funding for neural network research dried up almost overnight. Researchers moved away from the topic. The field entered what has come to be known as the first AI winter, a long period of reduced funding, reduced interest, and reduced progress. The dream that had seemed so close at Dartmouth was suddenly freezing over. And yet, in the shadows, a few stubborn, dedicated researchers kept working. They knew something that the broader academic community seemed to have forgotten. Minsky and Papert's critique applied to single-layer perceptrons, but what if you stacked multiple layers of perceptrons on top of each other? What if you created networks with input layers, hidden layers, and output layers? Such multi-layer networks could, in theory, solve problems that single-layer perceptrons could not, including the XOR problem. The challenge was figuring out how to train them. With a single-layer perceptron, it was clear how to adjust the weights. But with multiple layers, how do you know which weights in which layer to adjust when the network makes an error? This is where the story gets quiet for a while. Through the late 1960s, the 1970s, and into the early 1980s, neural network research was mostly out of favor. But a few researchers persisted. And in 1986, a breakthrough came. A paper by David Rumelhart, Geoffrey Hinton, and Ronald Williams demonstrated that an algorithm called backpropagation could efficiently train multi-layer neural networks. Backpropagation, which we will explore in more detail later, is a method for calculating how much each weight in the network contributed to the overall error, and adjusting all the weights accordingly. It works by propagating the error signal backwards through the network, from the output layer back to the input layer, adjusting each weight along the way. This was the key that had been missing. With backpropagation, you could train networks with multiple layers, networks that could solve complex problems that single-layer perceptrons could not. But even after backpropagation was rediscovered and popularized, the field did not immediately take off. There were still significant practical challenges. Training multi-layer networks required a lot of data and a lot of computing power. And in the 1980s and 90s, both were in short supply. The computers of the era were simply not fast enough to train large networks on large datasets in a reasonable amount of time. And the datasets themselves were limited. The internet had not yet exploded. Digital data was not yet ubiquitous. And collecting and labeling large datasets was expensive and time-consuming. So while the theoretical tools were now available, the practical infrastructure was not yet there. During this period, a trio of researchers who would later be called the godfathers of deep learning were doing work that would ultimately prove to be foundational. Geoffrey Hinton, based at the University of Toronto, continued to develop and refine neural network techniques, working on ideas like Boltzmann machines and deep belief networks. Yann LeCun, who would eventually lead AI research at Facebook, developed convolutional neural networks and applied them to practical problems like handwriting recognition. Yoshua Bengio, based at the University of Montreal, made fundamental contributions to the theory and practice of training deep networks. These three men, working largely independently but building on each other's ideas, kept the flame of neural network research alive during a period when most of the academic world had moved on. They were often denied funding, had their papers rejected from top conferences, and were told that they were wasting their time on a dead-end approach. But they persisted, and their persistence would eventually be vindicated in spectacular fashion. The moment everything changed, the moment that marks the beginning of the modern era of machine learning, can be pinpointed with remarkable precision. It happened in September of 2012 at the ImageNet Large-Scale Visual Recognition Challenge. ImageNet was a massive database of over 14 million labeled images, organized into more than 20,000 categories. Every year, teams of researchers competed to build the most accurate image classification system. For years, the winning systems had been based on traditional computer vision techniques, carefully hand-engineered features combined with relatively simple classifiers. And the progress had been steady but slow, with error rates declining by a percentage point or two each year. Then, in 2012, a team from the University of Toronto, led by Alex Krzyzewski and supervised by Geoffrey Hinton, entered a system called AlexNet. It was a deep convolutional neural network, the kind of system that Hinton and LeCun had been working on for decades. And it did not just win the competition, it destroyed the competition. Its error rate was nearly 11 percentage points lower than the next best system. To put that in context, the previous year's improvement had been less than 2 percentage points. AlexNet's margin of victory was unprecedented and unambiguous. Deep learning worked. It did not just work a little better than traditional methods. It worked dramatically, overwhelmingly, undeniably better. This moment was to machine learning what the Wright brothers' first flight was to aviation. It was proof of concept at a scale that could not be ignored. Within a year, virtually every major technology company had pivoted to deep learning. Google, Facebook, Microsoft, Amazon, Apple, Baidu, all of them began investing heavily in neural network research. Researchers who had been working on neural networks in obscurity for decades suddenly found themselves in enormous demand. Geoffrey Hinton was recruited by Google. Yann LeCun was recruited by Facebook. The AI winter was definitively over, and the AI spring had begun. And it was not just spring, it was a supernova. Now that we have traveled through the history, I want to bring you back to the present and explain as clearly and simply as I can what machine learning actually is. Not the history, not the hype, but the actual core idea. And I want to explain it in a way that you can carry with you. A mental model that makes everything else we discuss tonight click into place. Traditional computer programming works like this. A human programmer thinks about a problem, figures out the rules for solving it, and writes those rules down as code. The computer then follows those rules exactly. If you want a program that converts temperatures from Celsius to Fahrenheit, you write the rule, multiply by 9/5 and add 32. The computer follows this rule and gives you the correct answer every time. This works beautifully for problems where the rules are clear and well-defined. But there are many problems where the rules are not clear. How do you write a rule for recognizing a face? How do you write a rule for determining whether an email is spam? How do you write a rule for predicting whether a patient has cancer based on a medical scan? These problems are too complex, too nuanced, too dependent on subtle patterns that humans can recognize intuitively, but cannot easily articulate as explicit rules. Machine learning takes a completely different approach. Instead of having a human write the rules, machine learning has the machine discover the rules on its own by looking at data. You give the machine thousands or millions of examples, and the machine finds patterns in those examples that allow it to make predictions about new, unseen data. In the spam email case, instead of a human trying to write rules about which words or phrases indicate spam, you give the machine 10,000 examples of spam emails and 10,000 examples of legitimate emails, and the machine figures out for itself which patterns distinguish spam from legitimate email. Maybe it discovers that spam emails tend to contain certain combinations of words, tend to come from certain types of addresses, tend to have certain structural features. The machine discovers these rules on its own, from the data, without a human ever having to articulate them. This is a profound shift. For the entire history of computing up until this point, humans told machines what to do. With machine learning, machines figure out what to do by themselves, from experience. It is the difference between giving someone a fish and teaching them to fish. Except, in this case, you are not even teaching them to fish. You are throwing them in the water, and they figure out how to fish on their own. There are 3 things you need for machine learning to work. The first is data. Data is the raw material, the fuel, the food that feeds the learning process. Without data, there is nothing to learn from. The more data you have, generally speaking, the better the machine can learn. This is why the explosion of digital data over the past 2 decades has been so important for machine learning. We now generate more data in a single day than was generated in the entire history of humanity, up to the year 2000. Every search query, every social media post, every digital photograph, every online transaction, every sensor reading, all of it is data that can potentially be used to train machine learning systems. The second thing you need is an algorithm. The algorithm is the method, the procedure, the recipe that tells the machine how to learn from the data. There are many different machine learning algorithms, each with its own strengths and weaknesses, each suited to different kinds of problems. Some algorithms are simple and elegant, like linear regression. Others are immensely complex, like the deep neural networks that power modern language models. But they all share the same fundamental purpose. They are procedures for finding patterns in data. The third thing you need is a model. The model is the result of the learning process. When you apply an algorithm to a dataset, the output is a model, a mathematical representation of the patterns the machine has discovered. This model can then be used to make predictions about new data it has never seen before. Think of it this way. The data is the raw ingredients. The algorithm is the recipe. And the model is the finished dish. Once you have cooked the dish, you can serve it to anyone. Once you have trained a model, you can use it to make predictions about any new data you encounter. Let me use a simple analogy that ties back to what we discussed earlier about the brain. When a child learns to recognize cats, the data is all the cats and non-cats the child encounters. The algorithm is the learning process of the child's brain, the way neurons strengthen and weaken their connections in response to experience. And the model is the final state of the child's neural connections, the internal representation that allows the child to look at any new animal and determine whether it is a cat or not. Machine learning follows exactly the same structure, just with silicon and mathematics, instead of neurons and synapses. Now I want to walk you through the three main categories of machine learning. Think of these as three different styles of teaching. Each one is suited to different situations, and each one has its own strengths and limitations. The first category is called supervised learning, and it is the most common and probably the most intuitive. In supervised learning, you teach the machine by giving it examples that include both the input and the correct answer. It is like teaching with an answer key. You show the machine an image and tell it this is a cat. You show it another image and tell it this is a dog. You do this thousands or millions of times, with thousands or millions of labeled examples, and the machine gradually learns the patterns that distinguish cats from dogs. Then, when you show it a new image it has never seen before, it can predict whether it is a cat or a dog based on the patterns it has learned. The word supervised comes from the idea that there is a supervisor, a teacher, providing the correct answers during the learning process. Supervised learning is used for a wide range of practical applications. Email spam detection is a classic example. The machine is trained on millions of emails, each labeled as either spam or not spam, and it learns to distinguish between the two. Medical diagnosis is another important example. The machine is trained on thousands of medical images, each labeled by a human expert as showing or not showing a particular condition, and it learns to identify that condition in new images. Other examples include predicting house prices based on features like location, size, and age, predicting whether a customer will stop using a service, predicting whether a loan applicant will default, and much more. The second category is called unsupervised learning. In unsupervised learning, there is no teacher and no answer key. You give the machine a dataset and ask it to find patterns, structures, or groupings on its own. It is like handing someone a box of 1,000 puzzle pieces without showing them the picture on the box. They have to figure out how the pieces fit together by themselves. Unsupervised learning is particularly useful for discovering hidden structure in data. For example, imagine you have data about millions of customers, including their purchasing behavior, browsing habits, demographics, and more. You do not know in advance what groups exist within this data. You just know that not all customers are the same. Unsupervised learning can automatically discover clusters of similar customers, groups that share common behaviors or characteristics. Maybe it discovers that there is a group of price-sensitive bargain hunters, a group of brand-loyal premium shoppers, and a group of impulse buyers. These groups were hidden in the data all along, but no humans specified them. The machine found them on its own. Another important application of unsupervised learning is anomaly detection. This is the task of finding things that are unusual, that do not fit the normal pattern. This is incredibly valuable in areas like fraud detection, where you want to identify the one transaction out of millions that looks suspicious, or in manufacturing, where you want to identify the one product out of thousands that has a defect. In these cases, you do not have a catalog of every possible type of fraud or defect. You just know what normal looks like, and you want the machine to flag anything that deviates from normal. In the realm of space exploration, unsupervised learning has been particularly valuable. Astronomers collect vast datasets from telescopes and space probes, and much of this data has never been analyzed by human eyes. Unsupervised learning algorithms can sift through this data and find interesting patterns, unusual objects, or new classifications that humans had not previously identified. This is how some new types of galaxies and stellar phenomena have been discovered. The machine looked at the data without preconceptions, without being told what to look for. and it found things that humans had overlooked. The third category is called reinforcement learning, and it is perhaps the most fascinating of the three. Reinforcement learning is learning by doing. Instead of learning from a data set of examples, the machine learns by interacting with an environment, taking actions, and receiving feedback in the form of rewards or punishments. It is the closest analogy to how many animals, including humans, learn in the real world. Think about how you learned to walk as a child. Nobody gave you a data set of correct walking examples. Nobody supervised your training and told you this step is correct, this step is incorrect. Instead, you just tried. You stood up, wobbled, fell down. That was a negative experience, a kind of punishment signal. You tried again, adjusted your balance slightly, took a step, wobbled, maybe took another step, then fell again. Over time, through thousands of attempts, each one slightly adjusted based on the feedback from previous attempts, you learn to walk. Reinforcement learning works on exactly this principle. In reinforcement learning, there is an agent, which is the learner, and an environment, which is the world the agent interacts with. At each step, the agent observes the current state of the environment, chooses an action, and receives a reward or a punishment based on the outcome of that action. The goal of the agent is to learn a strategy, called a policy, that maximizes its total reward over time. The agent does not just try to get the most reward right now. It tries to get the most reward in the long run, which means it sometimes has to make short-term sacrifices for long-term gain. This is one of the most interesting and challenging aspects of reinforcement learning. One of the most famous examples of reinforcement learning is the game of Go. Go is an ancient board game that originated in China thousands of years ago. Despite having relatively simple rules, Go is a game of extraordinary complexity. The number of possible board positions in Go is greater than the number of atoms in the observable universe. For decades, building a computer program that could beat a professional human Go player was considered one of the grand challenges of artificial intelligence. Many experts believed it would not happen for at least 20 more years. Then, in 2016, a system called AlphaGo, developed by DeepMind, a division of Google, defeated Lee Sedol, one of the greatest Go players in history, in a 5-game match. AlphaGo won 4 games to 1. The impact of this achievement on the world of artificial intelligence cannot be overstated. It demonstrated that reinforcement learning, combined with deep neural networks, could achieve superhuman performance in tasks of extraordinary complexity. But what happened during the match was perhaps even more remarkable than the outcome. In the second game, AlphaGo made a move, Move 37, that shocked everyone watching, experts and amateurs alike. It was a move that no human player would have made. It seemed strange, almost nonsensical. But as the game unfolded, it became clear that Move 37 was not just good. It was brilliant. It was a move of such creativity and originality that Lee Sedol himself described it as beautiful. The machine had not just learned to play Go at a superhuman level. It had discovered strategies and ideas that were entirely new. Strategies that centuries of human Go playing had never produced. This was a profound moment. It suggested that machine learning was not just about copying human intelligence. It could go beyond it. It could discover things that humans had never thought of. Following AlphaGo's success, DeepMind created an even more remarkable system called AlphaZero. While AlphaGo had been trained partly on data from human games, AlphaZero started from nothing. It was given only the rules of the game and then played millions of games against itself, learning purely from its own experience through reinforcement learning. Within just a few hours, AlphaZero had surpassed all previous Go playing systems, including AlphaGo. And it did not stop at Go. AlphaZero also learned to play chess and shogi at a superhuman level, using the exact same algorithm. It was a stunning demonstration of the power and generality of reinforcement learning. In the context of health, reinforcement learning is being explored for some truly exciting applications. One of the most promising is in optimizing treatment plans. Consider a patient with a chronic disease like diabetes or cancer. The treatment is not a single event, but a long sequence of decisions. Which medication to use? What dosage? When to change medications? How to balance effectiveness against side effects? These decisions are made over time, and the outcome of each decision depends on all the decisions that came before. This is exactly the kind of sequential decision-making problem that reinforcement learning excels at. Researchers are developing systems that learn to optimize treatment plans by simulating thousands of possible treatment sequences and learning which strategies lead to the best patient outcomes. It is still early days, but the potential to improve patient care is enormous. Now that we have covered the three main categories of machine learning, I want to take you deeper into the technical details of how machines actually learn. Do not worry. We are going to go slowly, and I am going to explain everything with analogies and examples. You do not need a mathematics degree to understand this. You just need a bit of patience and curiosity. Let us start with the concept of a model. I mentioned earlier that a model is the output of the learning process, the mathematical representation of the patterns the machine has discovered. But what does a model actually look like? At its most basic level, a model is a mathematical function. It takes in some input, does some calculations, and produces an output. The simplest possible model is a straight line. You might remember from school the equation y equals mx plus b, where m is the slope of the line and b is the y-intercept, the point where the line crosses the vertical axis. This simple equation is actually a machine learning model. Given an input x, it predicts an output y. The goal of training this model is to find the values of m and b that make the best predictions for your particular data. For example, if you have data about the sizes of houses and their sale prices, you could fit a straight line to this data, where x is the size of the house and y is the predicted price. The slope m tells you how much the price increases for each additional unit of size, and the intercept b represents the base price. Finding the best values of m and b is the learning process for this simple model. Of course, most real-world problems are far too complex to be captured by a straight line. But the principle is exactly the same, whether you are fitting a straight line or training a neural network with billions of parameters. You have a model with adjustable parameters, and the learning process finds the parameter values that produce the best predictions. Now, how does the machine know whether its predictions are good or bad? This is where the concept of a cost function, sometimes called a loss function, comes in. The cost function is a measure of how wrong the model's predictions are. It compares the model's predictions to the actual, correct answers, and computes a number that represents the total error. The larger this number, the worse the model's predictions. The smaller this number, the better the model's predictions. The goal of training is to minimize the cost function, to find the parameter values that make the predictions as accurate as possible. Let me give you an analogy. Imagine you are trying to throw darts at a dartboard, and you are blindfolded. After each throw, someone tells you how far your dart landed from the bullseye. That distance is your cost, your error. Your goal is to adjust your throws to minimize this distance. After many throws, with feedback after each one, you gradually get better. You learn to compensate for your tendencies to throw too high or too far to the left. Machine learning works on the same principle. The model makes predictions. The cost function measures how far off those predictions are, and the learning algorithm adjusts the model's parameters to reduce the error. This process is repeated thousands or millions of times until the model's predictions are as accurate as they can be. This brings us to one of the most important algorithms in all of machine learning, an algorithm called gradient descent. Gradient descent is the workhorse of machine learning. It is the algorithm that actually does the learning, that actually adjusts the model's parameters to minimize the cost function. And despite its intimidating name, the basic idea behind it is beautifully simple. Imagine you are standing on a hilly landscape, and you want to reach the lowest point, the bottom of the deepest valley. But there is a catch. You are blindfolded. You cannot see the landscape. All you can do is feel the slope of the ground beneath your feet. What would you do? You would probably feel which direction goes downhill and take a step in that direction. Then you would feel the slope again, take another step downhill, and repeat. If you keep doing this, step after step, always moving in the direction of steepest descent, you will eventually reach the bottom of a valley. That is gradient descent. The landscape is the cost function. The height at any point represents the error of the model for a particular set of parameter values. The gradient is the slope, the direction of steepest ascent. Gradient descent moves in the opposite direction, the direction of steepest descent, toward lower error. The size of each step is controlled by something called the learning rate. If the learning rate is too large, you might overshoot the valley and end up bouncing back and forth without ever settling at the bottom. If the learning rate is too small, you will eventually get to the bottom. But it will take a very, very long time. Finding the right learning rate is one of the many art forms in machine learning. There is a subtlety here that is worth mentioning. In a complex landscape with many hills and valleys, gradient descent might lead you to the bottom of a local valley, rather than the deepest valley of all. You might think you have found the best possible set of parameters, when in fact there is an even better set somewhere else in the landscape. This is called the local minimum problem, and it is one of the challenges of gradient descent. Various techniques have been developed to address this, such as starting from random positions multiple times, or using variations of gradient descent that add a bit of randomness to help escape local minima. Let me pause here and connect this back to the human brain. When you learn something, your neurons adjust their connections, strengthening some and weakening others. This is conceptually identical to what gradient descent does. It adjusts the parameters of the model, making some larger and others smaller, in a way that reduces error. Your brain has its own version of a cost function, the feeling of surprise or wrongness when your expectations do not match reality. And it has its own version of gradient descent, the process of adjusting neural connections based on that error signal. The parallels between biological learning and machine learning are not just superficial. They run deep, and they are not a coincidence. Machine learning was explicitly inspired by what we know about how the brain works. Part 2. Now I want to explain what weights and biases are, because you will hear these terms a lot in any discussion of machine learning. In a neural network, each connection between neurons has a weight associated with it. The weight determines how strong that connection is, how much influence one neuron has on the next. A large positive weight means that neuron has a strong excitatory influence. A large negative weight means it has a strong inhibitory influence. A weight close to zero means the connection is weak and has little influence. During training, these weights are the parameters that get adjusted. When the network makes an error, the weights are updated slightly to reduce that error. After many rounds of training, the final values of the weights represent everything the network has learned. They are the network's knowledge, encoded in numbers. A bias is a slightly different concept. Each neuron in the network has a bias value, which is like a baseline level of activity. Even when all of the neuron's inputs are zero, the bias determines whether the neuron is inclined to fire or not. Think of it like a person's natural inclination. Some people are naturally optimistic, inclined to see the positive even when there is no specific reason. Others are naturally cautious, inclined to hold back. The bias captures this kind of baseline tendency. Together, the weights and biases of a neural network can number from a few dozen, for a tiny model, to hundreds of billions. For the largest models in existence today, there is a crucial concept in machine learning that I want to explain now, because it addresses one of the biggest challenges in the field. It is called overfitting. Overfitting occurs when a model learns the training data too well. This might sound like a good thing, but it is actually a serious problem. Imagine a student who prepares for an exam by memorizing all the answers to the practice tests. If the exam contains exactly the same questions as the practice tests, the student will get a perfect score. But if the exam contains new questions that test the same concepts in different ways, the student may fail miserably. The student has memorized specific answers rather than understanding the underlying concepts. Overfitting in machine learning is exactly the same. The model has memorized the specific patterns in the training data, including the noise and random fluctuations, rather than learning the true underlying patterns. When you then ask the model to make predictions on new data, it performs poorly because the noise and random fluctuations in the new data are different from those in the training data. The opposite problem is called underfitting, which occurs when the model is too simple to capture the true patterns in the data. It is like trying to draw a complex curve with a straight line. The straight line captures the general trend, but misses all the important details. The sweet spot in machine learning is a model that is complex enough to capture the true patterns in the data, but not so complex that it starts memorizing noise. Finding this sweet spot is one of the central challenges of machine learning, and a huge amount of research has gone into developing techniques for avoiding overfitting while still allowing the model to learn complex patterns. One of the most important of these techniques is the practice of splitting your data into separate sets for training, validation, and testing. The training set is what the model learns from. The validation set is used during training to monitor how well the model is generalizing, to check whether it is starting to overfit. And the test set is held out completely until the very end. The model never sees the test data during training. The performance of the model on the test set gives you an honest estimate of how well it will perform on truly new, unseen data. This practice is fundamental to good machine learning. Without it, you have no way of knowing whether your model has truly learned useful patterns or has merely memorized the training data. Now I want to take you into one of the most fascinating and powerful ideas in machine learning: neural networks. We have already talked about the history of neural networks, from the McCulloch-Pitts neuron to the perceptron to AlexNet. Now I want to explain how modern neural networks actually work, in detail, slowly, calmly, in a way that will make you feel like you truly understand them. A neural network is made up of layers of artificial neurons. The first layer is the input layer. This is where the data enters the network. If you are feeding the network an image, the input layer might have one neuron for each pixel in the image. If the image is 224 pixels by 224 pixels with 3 color channels, that is over 150,000 input neurons. Each neuron in the input layer holds the value of 1 pixel. The last layer is the output layer. This is where the network's prediction comes out. If the task is to classify an image into one of 1,000 categories, the output layer has 1,000 neurons, each representing the probability that the image belongs to that category. In between the input and output layers are the hidden layers. These are the layers where the actual computation happens, where the network transforms the raw input data into increasingly abstract and useful representations. The word hidden simply means that these layers are not directly visible to the outside world. You do not directly set the values of the hidden neurons or directly observe them. They are internal to the network. Here is how information flows through a neural network. The input data enters the input layer. Each input neuron passes its value to every neuron in the first hidden layer through weighted connections. Each neuron in the first hidden layer receives a weighted sum of all the inputs, adds its bias, and then applies an activation function to produce its output. This output is then passed to every neuron in the next hidden layer through another set of weighted connections. The process repeats, layer by layer, until the information reaches the output layer. The output layer applies its own activation function and produces the final prediction. This process of information flowing from input to output is called a forward pass. It is how the network makes a prediction for a given input. I want to take a moment to explain activation functions, because they are a small but crucial part of how neural networks work. An activation function is applied to the output of each neuron before it is passed to the next layer. Without activation functions, a neural network, no matter how many layers it had, would just be a very complicated way of computing a linear function. And a linear function, no matter how many layers you stack, is still just a linear function. It can only capture linear relationships in the data, like straight lines and flat planes. Most real-world relationships are not linear. They are curved, twisted, and complex. Activation functions introduce non-linearity into the network, allowing it to capture these complex relationships. There are several commonly used activation functions. The sigmoid function maps any input to a value between 0 and 1. It was one of the earliest activation functions used in neural networks, and is still used in certain situations, particularly when you want the output to represent a probability. The hyperbolic tangent function is similar to the sigmoid, but maps to values between -1 and +1. But the activation function that truly revolutionized deep learning is called ReLU, which stands for Rectified Linear Unit. ReLU is almost absurdly simple. If the input is positive, output the input unchanged. If the input is negative, output 0. That is it. Despite its simplicity, ReLU has several properties that make it extremely effective for training deep neural networks. It is computationally cheap. It helps alleviate the vanishing gradient problem, which we will discuss shortly. And it leads to sparse representations, where many neurons output 0, which can be beneficial for learning. The fact that something so simple could be so transformative is one of the beautiful surprises of machine learning. Now let us talk about how a neural network learns. We have already discussed the general principles, minimizing a cost function using gradient descent. But the specific mechanism by which gradient descent is applied to a neural network is called backpropagation. And it deserves a deeper explanation. Backpropagation is short for backward propagation of errors. The idea is straightforward. First, you do a forward pass, feed input data through the network, and get a prediction. Second, you calculate the error, the difference between the prediction and the correct answer. Third, you propagate this error backward through the network. From the output layer all the way back to the input layer, calculating along the way how much each weight contributed to the error. Fourth, you adjust each weight slightly in the direction that reduces the error. Then you repeat this process with the next piece of training data. Let me give you an analogy. Imagine a factory assembly line with many workers. The finished product at the end of the line is defective. You need to figure out which workers made mistakes and how to fix them. You start at the end of the line with the finished product and trace the error backward. The final worker says, "The problem was with the component I received from the worker before me." That worker says the same about the worker before them. Eventually, you trace the error back through every station on the line, and you know exactly how much each worker contributed to the final defect. You then tell each worker to adjust their work slightly to reduce the defect. This is backpropagation. The output error is propagated backward through the layers of the network, and each weight is adjusted based on its contribution to the error. One of the challenges of training deep networks is the vanishing gradient problem. As the error signal propagates backward through many layers, it can get smaller and smaller, until by the time it reaches the early layers, it is effectively zero. This means the early layers barely learn at all, while the later layers do all the learning. It is like a game of telephone, where the message gets garbled as it passes through many people. By the end, the original message is lost. This problem was one of the main reasons why deep neural networks were difficult to train for so long. The solutions that have been developed, including careful initialization of weights, the use of ReLU activation functions, batch normalization, and residual connections, have been crucial in enabling the training of very deep networks with dozens, hundreds, or even thousands of layers. Let me now explain some specific types of neural networks, because different types are designed for different kinds of data and different kinds of tasks. Convolutional neural networks, or CNNs, are designed specifically for processing images and other grid-like data. The key idea behind CNNs is that they use small filters, also called kernels, that slide across the image and detect local features. Think of it like looking at a photograph through a small magnifying glass. You move the magnifying glass across the photo, and at each position, you observe what is in that small region. Each filter is designed to detect a specific kind of feature, like a horizontal edge, a vertical edge, a particular color gradient, or a specific texture. In the first layer of a CNN, the filters detect very simple, low-level features like edges and corners. In the second layer, these simple features are combined to detect more complex features like shapes and textures. In the third layer, these shapes and textures are combined to detect parts of objects, like an eye, a wheel, or a wing. In the fourth layer, these parts are combined to detect whole objects, like a face, a car, or a bird. This hierarchical, bottom-up construction of increasingly complex features from simple building blocks is extraordinarily powerful. And remarkably, it mirrors how the human visual cortex processes images. Your brain's visual processing system has multiple layers, called V1, V2, V3, V4, and so on, each of which processes increasingly complex visual features. The early layers detect edges and orientations. The later layers detect faces, objects, and scenes. When computer scientists designed CNNs, they were directly inspired by what neuroscientists had discovered about the brain's visual system. And when they found that this approach worked incredibly well for machine vision, it was a beautiful confirmation of the deep connection between biological and artificial intelligence. Between the convolutional layers, CNNs typically include pooling layers. A pooling layer reduces the size of the data by summarizing small regions. For example, a max pooling layer takes a small region, say 2 pixels by 2 pixels, and replaces it with the maximum value in that region. This reduces the spatial dimensions of the data by half, while retaining the most important features. Pooling helps make the network more efficient and helps it become invariant to small translations, meaning the network can recognize a cat whether it is in the left half of the image or the right half, slightly higher or slightly lower. CNNs have been spectacularly successful in a wide range of applications. In medical imaging, CNNs can detect diseases from X-rays, MRIs, and CT scans with accuracy that rivals or exceeds that of human specialists. In autonomous driving, CNNs process the images from the car's cameras to detect pedestrians, other vehicles, traffic signs, lane markings, and obstacles. In satellite imagery, CNNs can identify buildings, roads, crops, forests, and water bodies, enabling applications from urban planning to environmental monitoring. In security, CNNs power facial recognition systems that can identify individuals in real time from video feeds. Recurrent neural networks, or RNNs, are designed for sequential data where the order matters. Language is a perfect example. The meaning of a sentence depends not just on the individual words, but on the order in which they appear. The dog bit the man, and the man bit the dog contain exactly the same words, but have very different meanings. RNNs handle this by maintaining a hidden state, a kind of memory, that gets updated at each step of the sequence. When processing a sentence, NRUN reads one word at a time, and at each step it updates its hidden state based on the current word and the previous hidden state. This allows information from earlier in the sequence to influence the processing of later elements. However, basic RNNs suffer from the vanishing gradient problem we discussed earlier. When sequences are long, the information from early in the sequence tends to fade away, making it difficult for the network to capture long-range dependencies. This problem was addressed by a special type of REN called long short-term memory, or LSTM. LSTMs were introduced by Sepp Hochreiter and Jürgen Schmidhuber in 1997. They include special mechanisms called gates that control the flow of information, allowing the network to selectively remember or forget information from earlier in the sequence. Think of it like a person who has a notepad. At each step, they can choose to write something new on the notepad, erase something old, or read from the notepad to help with the current task. This selective memory mechanism allows LSTMs to capture dependencies over very long sequences, making them much more powerful than basic RNNs. LSTMs have been used successfully for speech recognition, language modeling, machine translation, and time series prediction. In healthcare, LSTMs are used to analyze sequences of medical events, like a patient's history of symptoms, medications, and test results, to predict future health outcomes. But the most transformative neural network architecture to emerge in recent years is, without question, the transformer. The transformer architecture was introduced in a paper published in 2017 by a team at Google, with the title, "Attention is All You Need." This paper is widely considered one of the most important in the history of artificial intelligence. The key innovation of the transformer is the attention mechanism. Let me explain what attention means in this context. When you read a sentence, you do not pay equal attention to every word. Some words are more important than others for understanding the meaning. If I say the cat sat on the mat because it was tired, the word it refers to the cat, not the mat. You know this because you pay attention to the context, to the semantic relationships between the words. The attention mechanism in a transformer does something similar. For each element in the input, it calculates how much attention to pay to every other element. This allows the model to capture relationships between any two positions in the sequence, regardless of how far apart they are. Unlike RNNs, which process sequences one element at a time, transformers process the entire sequence at once, in parallel. This makes them much faster to train, especially on modern hardware that excels at parallel computation. The transformer architecture is the foundation of all modern large language models. GPT, which stands for Generative Pre-trained Transformer, is a series of models developed by OpenAI that use the transformer architecture. BERT, which stands for Bidirectional Encoder Representations from Transformers, was developed by Google and is used for understanding the meaning of text. Claude, the model developed by Anthropic, is also based on the transformer architecture. These models are trained on vast amounts of text data, billions of web pages, books, articles, and conversations, and they learn to predict the next word in a sequence. This might seem like a simple task, but it turns out that learning to predict the next word requires the model to develop a deep understanding of language, including grammar, facts about the world, reasoning abilities, and even a form of common sense. The capabilities that emerge from this training process are remarkable. Modern language models can write essays, answer questions, translate between languages, summarize long documents, write computer code, compose poetry, explain complex concepts, and engage in extended conversations on virtually any topic. Many of these capabilities were not explicitly programmed or anticipated by the model's creators. They emerged naturally from the process of training on large amounts of data. This phenomenon, where capabilities appear that were not explicitly trained for, is called emergence, and it is one of the most fascinating and least understood aspects of modern machine learning. There is another type of neural network that I want to tell you about, because it represents a fundamentally different approach to generating data. It is called a generative adversarial network, or GAN. GANs were introduced by Ian Goodfellow in 2014, and the idea behind them is brilliantly creative. A GAN consists of two neural networks that are pitted against each other. The first network is called the generator. Its job is to create fake data that looks real. The second network is called the discriminator. Its job is to tell the difference between real data and the fake data produced by the generator. The two networks are trained simultaneously in a competitive process. The generator tries to get better at fooling the discriminator, and the discriminator tries to get better at catching fakes. Over time, this adversarial process pushes both networks to improve. The generator gets better and better at creating realistic data, and the discriminator gets better and better at detecting fakes. When the training process is successful, the generator becomes so good that its output is virtually indistinguishable from real data. GANs have been used to generate stunningly realistic images of people who do not exist, to create artwork, to transform photographs, and to generate synthetic data for training other models. In healthcare, GANs have a particularly valuable application. Medical data is often scarce and sensitive. Privacy regulations rightfully limit the sharing of patient data. But machine learning models need large amounts of data to learn effectively. GANs can be used to generate synthetic medical data, data that looks and behaves like real patient data, but does not correspond to any actual patient. This allows researchers to train machine learning models without compromising patient privacy. It is an elegant solution to a significant problem. Now I want to shift our focus to something that often gets overlooked in discussions of machine learning, but is arguably the most important factor of all. Data. Without data, machine learning does not exist. You can have the most sophisticated algorithm in the world, running on the most powerful computer in the world, but without data to learn from, it is useless. Data is the oxygen that machine learning breathes. The explosion of data over the past 2 decades has been one of the primary drivers of machine learning's success. Consider some numbers. Every day, the world generates approximately 2.5 quintillion bytes of data. That is a 2 followed by 18 zeros. This data comes from everywhere. Every search query you type, every photo you take, every message you send, every video you watch, every purchase you make, every step you take while carrying your phone, all of it generates data. Social media platforms collectively generate hundreds of millions of posts, images, and videos every day. Sensors embedded in everything from factory equipment to household appliances generate continuous streams of data. Medical devices, satellites, traffic cameras, weather stations, all of them are generating data constantly. We are living in an era of unprecedented data abundance, and this abundance is the fuel that powers the machine learning revolution. Data comes in different forms, and it is useful to understand the main categories. Structured data is data that is organized in a well-defined format, like a spreadsheet or a database table. Each row represents an observation, and each column represents a feature. Examples include financial records, demographic information, and inventory databases. Structured data is relatively easy for machines to work with because it is already organized. Unstructured data is data that does not have a predefined format. It includes text, images, audio, and video. An email is unstructured data. A photograph is unstructured data. A voice recording is unstructured data. Unstructured data makes up an estimated 80% of all the data in the world. And it is much harder for machines to work with, because it requires sophisticated processing to extract useful information. Semi-structured data falls somewhere in between. It has some organizational elements, but does not conform to a strict schema. Examples include JSON files, XML documents, and web pages. Semi-structured data has some structure that helps with processing, but is more flexible than fully structured data. One of the most important developments in machine learning has been the ability to work with unstructured data. The breakthroughs in computer vision that allow machines to understand images, the breakthroughs in natural language processing that allow machines to understand text, the breakthroughs in speech recognition that allow machines to understand spoken words. These all come down to developing machine learning techniques that can extract patterns from unstructured data. And since unstructured data is the vast majority of all data, these breakthroughs have opened up an enormous range of applications. But data quantity alone is not enough. Data quality matters just as much, and in many cases, even more. There is a saying in machine learning that has become almost a cliché because it is so true. Garbage in, garbage out. If you train a model on bad data, you will get a bad model, no matter how sophisticated your algorithm is. Bad data can mean many things. It can mean data with errors, missing values, or inconsistencies. It can mean data that is not representative of the real-world situation you are trying to model. And critically, it can mean data that contains biases. Bias in data is one of the most serious and challenging issues in machine learning, and it deserves careful attention. Machine learning models learn from historical data, and historical data reflects historical realities, including prejudices and inequities. If a hiring algorithm is trained on a company's past hiring data, and that company has historically hired mostly men for technical roles, the algorithm may learn to prefer male candidates, not because maleness is a predictor of job performance, but because it was a pattern in the historical data. This is not a hypothetical example. It actually happened at a major technology company, and the tool had to be scrapped. If a criminal risk assessment algorithm is trained on historical arrest data, and certain communities have been disproportionately policed, the algorithm may assign higher risk scores to individuals from those communities, perpetuating and amplifying existing inequities. If a medical algorithm is trained predominantly on data from one demographic group, it may perform poorly for other groups. A study found that a widely used commercial algorithm for predicting healthcare needs was systematically underestimating the needs of Black patients because it used healthcare spending as a proxy for health needs. And Black patients had historically spent less on healthcare due to systemic barriers to access. These are not just technical problems. They are ethical problems with real consequences for real people. And they illustrate a fundamental truth about machine learning. The technology itself is neutral, but the data it learns from is not. The data carries the imprint of the society that generated it, with all its biases and imperfections. Building fair and equitable machine learning systems requires not just technical expertise, but also awareness of social context, careful examination of data for biases, and ongoing monitoring of model outputs for disparate impacts. The practical work of preparing data for machine learning is often unglamorous but absolutely essential. Data cleaning involves identifying and correcting errors, filling in missing values, and resolving inconsistencies. Data preprocessing involves transforming data into a format suitable for the learning algorithm, which might include normalizing numerical values, encoding categorical variables, or resizing images. Data augmentation involves artificially increasing the size of the training dataset by applying transformations to existing data, like rotating or flipping images, which helps the model learn to be invariant to these transformations. In many machine learning projects, data preparation takes up 80% or more of the total effort. The glamorous part, building and training the model, is often a relatively small fraction of the work. When we talk about data in the modern context, we inevitably encounter the concept of big data. Big data refers to datasets that are so large, so fast-moving, or so varied that they cannot be processed using traditional methods. Big data is typically characterized by three properties known as the 3 V's. Volume refers to the sheer size of the data, often terabytes, or petabytes, or even more. Velocity refers to the speed at which new data is generated and needs to be processed, sometimes in real time. Variety refers to the many different types and sources of data. Handling big data requires specialized tools and infrastructure. Frameworks like Hadoop and Spark allow data to be distributed across many machines and processed in parallel. Cloud computing platforms like Amazon Web Services, Google Cloud, and Microsoft Azure provide the computing resources needed to store and process massive datasets without requiring organizations to build and maintain their own data centers. In the realm of space exploration, big data is not just a buzzword. It is a fundamental reality. The Square Kilometre Array, a massive radio telescope currently under construction, is expected to generate more data per day than the entire global internet traffic. Analyzing this flood of data will require machine learning algorithms running on enormous computing clusters. Without machine learning, much of this data would be unusable, simply too vast for humans to analyze. The intersection of data and privacy is one of the defining issues of our time. Every day, vast amounts of personal data are collected by companies, governments, and other organizations. This data is valuable for machine learning, but it also represents a profound invasion of privacy if mishandled. Health data is perhaps the most sensitive category of all. Your medical records, your genetic information, your fitness tracking data. These paint an incredibly intimate portrait of your life. And the idea of this data being used without your knowledge or consent is deeply troubling. Regulations like the General Data Protection Regulation in Europe and the California Consumer Privacy Act in the United States are attempts to give individuals more control over their personal data. But the technological and legal landscape is evolving rapidly, and the balance between the benefits of data-driven innovation and the protection of individual privacy remains a work in progress. Let us now turn to one of the most exciting and impactful areas where machine learning is making a real difference in people's lives. Healthcare. This is where the abstract concepts we have been discussing become deeply personal, because healthcare affects every single one of us. The promise of machine learning in healthcare is simple and powerful. It will not replace doctors. It will make them better. A doctor, no matter how experienced and skilled, is limited by the number of patients they can see, the number of papers they can read, the amount of data they can hold in their mind at any one time. Machine learning has no such limitations. It can analyze millions of patient records in seconds. It can read every medical paper ever published. It can hold in its digital memory every symptom, every diagnosis, every treatment outcome. The combination of human empathy and judgment with machine speed and precision is greater than either alone. The area where machine learning has had its most dramatic impact in healthcare is medical imaging. Radiologists, the doctors who read X-rays, CT scans, MRIs, and other medical images, spend their careers developing the ability to detect subtle abnormalities in these images. It takes many years of training and thousands of cases to become proficient, and even the best radiologists can miss things, especially when they are tired, rushed, or when the abnormality is particularly subtle. Machine learning systems, specifically convolutional neural networks, have been trained on millions of medical images, each labeled by expert radiologists. These systems have learned to detect a wide range of conditions with remarkable accuracy. In detecting diabetic retinopathy, a common complication of diabetes that can lead to blindness, Google's DeepMind developed an AI system that was shown to perform as well as expert ophthalmologists. The system analyzes images of the retina, the light-sensitive tissue at the back of the eye, and identifies signs of the disease, enabling early treatment that can prevent vision loss. In detecting breast cancer from mammograms, machine learning systems have been shown to reduce both false positives and false negatives. A landmark study, published in the journal Nature, showed that an AI system developed by Google Health achieved accuracy that was superior to that of individual radiologists. In detecting lung cancer from CT scans, machine learning is proving particularly valuable because early detection of lung cancer dramatically improves survival rates. Low-dose CT scans can detect lung nodules, small growths in the lungs that may be cancerous. But not all nodules are cancerous, and determining which ones need further investigation is a challenging task. Machine learning models can analyze the size, shape, density, and growth rate of nodules, and predict with high accuracy which ones are likely to be malignant. This helps doctors make better decisions about when to intervene and when to simply monitor. In detecting brain tumors, machine learning can precisely segment tumor boundaries in MRI scans, creating detailed three-dimensional maps that help surgeons plan their approach. Accurate segmentation is critical because the goal is to remove as much of the tumor as possible while preserving healthy brain tissue. Machine learning can also predict tumor type and grade from imaging alone, which can inform treatment decisions before surgery or biopsy. Skin cancer detection is another area where machine learning has shown impressive results. A study published in the journal Nature in 2017 showed that a convolutional neural network trained on over 100,000 skin lesion images could classify skin cancers with accuracy comparable to board-certified dermatologists. The potential implications are enormous. Skin cancer is the most common form of cancer worldwide, and early detection is the key to successful treatment. A machine learning system that can accurately assess skin lesions from photographs could bring expert-level screening to millions of people who currently lack access to dermatologists, particularly in rural and underserved areas. But I want to be very clear about something. The best results in medical imaging come not from AI alone, but from AI working alongside human doctors. Study after study has shown that the combination of AI and human radiologists is more accurate than either alone. The AI catches things the human misses, and the human catches things the AI misses. It is not a competition. It is a collaboration. And this collaborative model is likely how AI will be integrated into healthcare for the foreseeable future. Beyond medical imaging, machine learning is revolutionizing drug discovery. The traditional process of developing a new drug is extraordinarily long and expensive. It typically takes 10 to 15 years and costs an average of over $2 billion. The process involves identifying potential drug candidates, testing them in laboratory settings, testing them in animal models, and then conducting multiple phases of clinical trials in humans. Most potential drugs fail at some point in this process. In fact, the success rate of drugs entering clinical trials is less than 10%. Machine learning can accelerate this process at multiple stages. In the earliest stage, identifying potential drug candidates, machine learning can screen millions of chemical compounds virtually, predicting which ones are most likely to interact with a specific biological target. This dramatically reduces the number of compounds that need to be physically synthesized and tested in the laboratory, saving enormous amounts of time and money. Machine learning can also predict the properties of drug candidates, such as their toxicity, their ability to be absorbed by the body, and their potential for side effects, allowing researchers to focus on the most promising candidates early in the process.